All right, let's carry on. So ICMP sends pings to see if somebody's listening, and it also sends other error conditions like when a packet is discarded because the time to live is expired because it can't find it, and so on. So Traceroute uses ICMP, or it can use other protocols like UDP. You set a series of packets, one with a TTL of 1, so that the first router, it will time out, and you'll send an ICMP timeout message. Then you send one with TTL2 and TTL3, and that way you can trace out all the hops from here to a server to help diagnose a problem somewhere on the route. All right, so Unix and Cisco use UDP, and Microsoft sends ICMP. They're both carried over IP, and it's IP where the TTL is. So, all right, Telnet is used to send commands to a command line client. It is not encrypted. It is therefore unsafe to be used anymore, and everybody should have blocked it long ago, but a bunch of people continue to use Telnet and FTP even though they're not encrypted, which is ridiculous. What you should use instead is SSH, which encrypts your data so people cannot read it or modify it. FTP sends files back and forth, but again, it sends passwords and files without any encryption, and it uses ports in a very strange way, which messes up firewalls because it uses an arbitrary high-numbered port. So FTP, like Telnet, really should be considered obsolete, and everybody should quit using it. What you should do is use SFTP, which sends your FTP data over SSH, or one of the other encrypted protocols. TFTP is used to send files, and there's no password at all. FTP uses a plain text password sent over the internet unsafely, but TFTP uses no password at all. The idea is to have a wire connecting directly to one device, not on the internet, and upload firmware into a phone or something, but unfortunately it was carried over the internet and used to spread worms up through Windows 2000 or so. It's why they added a firewall in Windows XP. Anyway, all right. SSH is the secure replacement for Telnet, like we said, and it replaces all the FTP and R commands like rlogin and rshell. You can send files, and you can copy files over the internet over SSH with it, and you can use it as a secure tunnel for other protocols. So SSH is very commonly used to control Unix servers, and now it's included in Microsoft in PowerShell. At least you can add it in. SMTP sends email between servers. POP and IMAP receive email from servers down to a local client like Outlook Express it used to be, and I guess some people are still using Outlook. All these run without encryption, but there are encrypted versions of them that run on other ports. DNS resolves alphabetic names like ccsf.edu down to IP addresses, and the most common form uses UDP 53, although it can also use TCP 53, and that's what's used by the more modern system that uses DNSSEC to sign the records, which provides a kind of authentication and security, and it also makes the responses too big to move over UDP because for some ridiculous reason, the UDP-based version of DNS is limited to a maximum packet size of 512 bytes. For no reason, UDP can carry a larger one, but they just put in that limitation, and you have to use TCP for the larger one. So there are various types of DNS servers. Every domain has a start of authority, and this is the master record for a zone. So CCSF's start of authority is where you will have, if you add a new server to the CCSF domain, you'll put it on the start of authority, and it will then get copied to other services. And yes, I see another comment there about DOE. DNS over HTTPS is DOE, which is a popular way to add encryption to DNS, which is missing in the original protocol. There are recursive servers, which is what your router at home is. You ask it where yahoo.com is, and it doesn't know, but it asks somebody else and finds it for you, so it finds the answer. Caching servers store recently resolved names so you don't have to ask again for more performance. And DNS has a lot of weaknesses. It uses UDP, which does not have a handshake and can be used as a mechanism for packet amplification, denial of service, because you can send a DNS request with somebody else's address in the from address, and they will then get the reply. So you can flood them with unknown traffic. No authentication. The security requires is the only way your traffic is distinguished from other people's traffic is from a source port and a query ID. And if attackers can guess both of these numbers, they can poison a DNS server's cache, which is the Kaminsky attack. The famous Dan Kaminsky, that's what made him famous, was finding a weakness in DNS that you could use to reroute traffic on the internet. So the cure is DNSSEC, which is slowly rolling out across the internet, where there will now be authentication and integrity to DNS responses, although not encryption. So it uses public key encryption and adds a signature to the DNS responses so that when you get a reply, when one server gets data from another server, it can cryptographically verify that it got it from an authorized server and not from some attacker trying to lie. So if you want to observe this stuff, you can use an online dig client called a looking glass. There's a bunch of these because typically your local area network will not handle all the advanced DNS features. And so you can look here at a looking glass and you can do a query at ietf.org. And then I got an ietf.org answer, and here I got the cryptographic signatures, this long base64 junk. That is the signature, which a DNS resolver that is verifying signatures would be able to verify that I indeed got that really from the authorized start of authority for IETF and not from somebody else. SNMP is used to control devices like firewalls and servers over the network. In the early versions, sent these passwords called community strings in plain text without encryption, which is a terrible idea, and most people always left them at their default values anyway, of public and private. So like so many of these protocols, the early version was ridiculously insecure. There is a newer version that adds encryption and is much better, but many people continue to use the old version that is not safe because they have legacy hardware that is using the old version and they don't feel like replacing it. HTTP sends web pages over again with no encryption. It is not recommended anymore for any purpose because even if you view a normal simple page over HTTP without any login or credit card number or anything, if it's not encrypted, anybody can add JavaScript to that page as it passes by, anybody with a man-in-the-middle position, and so they can attack your browser. So everything really should be using HTTPS these days, and a very large amount of websites have pretty much switched to HTTPS after Google did it first. And then everything's encrypted, everything's authenticated, and a whole bunch of attacks are prevented. BootP was an old way to get a IP address from the network before DHCP. It's pretty much been replaced by DHCP. And DHCP is what happens when you boot up your laptop. It has a MAC address built in, but it does not know what IP address to use because it doesn't know what network you're going to connect it to. And when you connect it to a network, it then sends out a broadcast request, well, can I please have an IP address? And then the DHCP server gives your laptop an IP address. All right, so let's look at 4D. And supposedly, I've got all these things fixed so they won't be too slow anymore. 4D, play, okay? Well, I'll give it a few more seconds, but maybe you'll, okay, good. There may be one more. maybe not. Ah, there we go. All right. All right. So which utility sends packets with different TTLs? Okay, that's Traceroute. All right. And which one sends file transfers with no password? TFTP. FTP has a password. It sends it unsafely, but there is a password. TFTP has no password at all. So it turned out to be extremely handy for putting malware on systems. All right, which protocol runs on port 22? All right, that's SSH. All right, and which protocol has RRSig? Yep, that's DNSSEC, to sign the resource records so you know who they came from. All right, Ortega. All right, 4D42 was one before, but I don't know who they are. And POG. I don't think we know who that is either. All right, so I think I'll do one more, make it a little longer than usual, but this is kind of a long chapter, and I don't want to leave too much of it for next time, so we'll go up to one more Kahoot. All right, so at layer 1, some of your cabling terms, you can have electromagnetic interference, where external electric signals, like from fluorescent lights, leak in and affect the signal in the wire, or leak from one wire to another. So that's electromagnetic interference coming from the outside, crosstalk from one wire to the other, and attenuation, as the resistance in the wire causes the signal to fade as you go down the wire. Those are some of the limitations of wires. But most people use the cheapest and most common kind of cable is unshielded twisted pair. You have 4 pairs of wires twisted together to help cancel out the crosstalk, and with a different number of turns per inch for each 4 of them, again to cancel out the crosstalk, and just plastic on the outside, no protection from external sources of EMI. And so there's different categories of cable. The most common these days is Cat 6. Most people are using it, which now you can run any speed through a cable if it's short enough. The only issue is when it gets long, and if you use Cat 6, you can run gigabit even out to the full length, which is 100 meters. Shielded twisted pair just adds a layer of tinfoil on the outside like a coax, so now it's protected from external EMI. It's also stiffer and hard to bend around a corner and a little more expensive, so it's not as commonly used, but it is an option if you're in an area with electromagnetic interference. And then to have better protection, use coax, which is what your cable internet is using. You have one conductor in the middle and one braided sheath on the outside and plastic protecting it. And so this makes a perfect waveguide, a cylindrical waveguide which can very efficiently move a lot of data through. Typo on this slide, electromagnetic? Oh, Thank you for telling me. Let me go back and see. Oh, you're right. Why, thank you. Might as well fix it while I'm here. Good. That's not fixing it. That's fixing it. Good. All right. So, this is very resistant to electromagnetic interference and gives you a higher bandwidth too. And the best thing of all is fiber optics. The network receivers and detectors are more expensive, although the cable is not, and it can send signals very far and immune for electromagnetic interference. The problem is you have to keep the ends clean, and it costs more money to repair breaks and such. So there's multimode fiber, which has a 50 micron or 62.5 micron core, so you can feed it with cheap LEDs, but the light can pass through multiple paths, so it tends to smear out and you have less total bandwidth. Single mode fiber has a core of just a few microns across. It is essentially a perfect waveguide, like a coax cable, for infrared light and can carry an enormous amount of data. And that's what's used for long undersea cables, where they use wavelength division multiplexing to send many different colors of infrared through the same cable to move more data through, and you can get to very high data transmission, like 10 gigabits per second, or even much higher, through single mode fiber optics. All right, so Ethernet is the ubiquitous network everybody uses for local area networks these days. Originally it used coaxial cables and a physical bus. Now it uses a physical star with twisted pair cables, where you have one central device, which is a switch, or sometimes a switch and a router combined, and every individual device has a cable going into it. So this was the coax stuff, 10 base 2 and 10 base 5. That stuff is long gone. Now we're all using 100 base T or 1000 base T, which can move at 100 megabits per second or a gigabit. CSMA CD is the technique used for wired Ethernet, and it doesn't really matter about the collisions, except back in the days when we used hubs instead of switches, which are also pretty much extinct. But this would send data, and if two devices tried to send at the same time, the overlapping electrical signals would cause unusually high or low voltage, and they would detect that, and then they would send a jamming signal and wait and resend the packets. So you'd have a collision event and a retransmission of data. All right. What's used on wireless networks is collision avoidance, since there's no way to detect a collision because the electric signal is attenuating over distance. So you use collision avoidance. Before you talk, you say, all right, everybody shut up, I'm going to talk. Then you send your data. Then you say, okay, now you can talk. So half of the bandwidth on your wireless network is spent arguing about who's going to talk next. But the end result is you can communicate over a network where collisions cannot be detected and fixed, so you have to avoid them. And I think wireless networks, I don't know if you can send and receive at the same time on a wireless network physically. You can over an Ethernet cable. I think you can send and receive at the same time over a wireless network too, but I'm not absolutely sure now that you mention it. All right, ArcNet and Token Ring are older signals that ran at low rates. These were some of the early local area network technologies. These used tokens, so there were no collisions. You'd have a token going through the network, and it would come to you, and you could only send data when the token came to you. So you get your chance to talk, and then you'd have to wait for another chance to talk, and that way there was never any issue of two people talking at the same time. FDDI was another legacy line technology with two fiber rings. It had one fiber ring going clockwise and one going counterclockwise, and the point of that is if you had one cut in the wire, you could still send data by sending it the other way to go around the cut. So, but it ran at 100 megs and was again slow and obsolete. All right, so the physical topologies, you can have a bus like this. That's the old one, but it means a single cable break will isolate part of the network, and this is not used much anymore. A tree or hierarchical you can have with this sort of thing, and this is what's actually used sometimes between buildings at campuses. And a ring was FDDI, and several of these actually had everything in a ring, and sometimes a double ring so you could withstand one cut. These are again rarely used anymore. What's almost always used is a star. You have a central device like a switch, and everybody goes to the switch, But you actually have these other topologies when you're connecting your switches from one building to switches in another floor or another building. At that layer, it might use one of these other topologies. And there's a mesh, which is what's used on the internet, where you have more than one route. So you could go this way, or you could go that way, or you could go this way. And the internet is a partial mesh where there's not every device connected to every other device, but there are redundant connections, so quite a few links can fail, and you'll still find a way to go around and get there. All right, so let's take a look at 4E, which is here. All right. I think we might have one more. Yeah, now this is the same group of people we've had. All right. All right. So what happens when you put your cables near a fluorescent light? I see a typo in the question, but not too bad. Yep, electromagnetic interference. All right. Okay, what's the most common kind of cable? Yep, UTP, unshielded twisted pair, is common Ethernet cable. All right, which LAN has 2 fiber rings? That's FIDI, an old protocol. I've never seen it or used it. All right. All right, what physical topology is used by Ethernet LANs? It's a star, physical star. Each device has its own cable going into the switch. All right. All right. Uh-huh. All right. Good. And I think A, B, C, D, E. I think that's enough. I think we'll leave it there for this time. Let me make a note where I left off. I'll stop the video.